I was in 7th grade, it was still possible for teachers to do things which these days would be considered cruel and unusual, because they were cruel and unusual. Here's an example. When I was in 7th grade, I had a particular teacher that if you were talking in class, here's what he did. He would make you stand next to the wall, put your arms out, and then he would take a pretty heavy book and put it on top of your hands like so, and he would make you stay there for 10, 15 minutes. Basically, until you started physically breaking down, and it did have the result of students not talking so much, but it was a pretty painful experience. Let's look just how painful it was. That's a physics question that we can answer right now. Here's a problem statement. A person of average size has arms of mass 4 kilograms with the center of mass approximate the elbow, 25 centimeters from the shoulder joint. A student extends both arms straight out from his body. Now he supports a 5-kilogram dictionary with both hands 50 centimeters from the shoulder joint. By what factor does this increase the torque about the shoulder joint? Let's look at the problem and extract the crucial pieces of information. Well, first off, we need data about a person's arms. And we're told the mass of the arms is 4 kilograms, and the center of mass of the arms, 25 centimeters from the shoulder joint. Now, to this situation is added a dictionary, which has mass 5 kilograms, and it's added 50 centimeters from the shoulder joint. That's the data we need from the problem. Let's go ahead and do the physical setup. Let's draw a picture of the situation. Here's an arm held horizontally, and here's the shoulder joint. And this is ultimately a torque question. We are asked to compute the torque, and we're going to compute the torques about the shoulder joint. We always have to compute torques around a particular point. They're going to be torques about the shoulder joint. And there's a couple of things that contribute to the torque. One is the weight of the arm itself, and 2 is the weight of the dictionary. Now remember, torque is equal to a distance times the force times the sine of an angle. The 2 forces that we have are the weight of the arm and the weight of the dictionary. So those are going to be the values that we use for F. But we need to consider, what do we use for the distances R? We're going to start with the arm. To compute the gravitational torque due to the arm's weight, what distance do we use? We'll give you some choices. Gravitational torque is always figured at the center of mass. And so we have the weight of the arm. We imagine that entire force is acting at the center of mass. So the distance that we use, the distance R, is the distance from the pivot point, the shoulder joint, to the center of mass of the arm. And we're told that's 25 centimeters, or 0.25 meters. That's the distance we use for this torque. But how about for the book? To compute the gravitational torque due to the book's weight, what distance do we use? We'll give you some choices. The book is out at the end of the arm, 50 centimeters from the shoulder joint. So it's 50 centimeters from the point about which we compute the torques. So in the case of the book's weight, the distance we use, 50 centimeters, 0.50 meters. That's what we use in that case. Now another element of the puzzle is the angle. But in both cases, the angle between the line from where the force is applied to the pivot point is 90 degrees. And since we have 90-degree angles, sine of phi in both cases is equal to 1. And so this term just goes out of the equation. So in both cases, the torque is just equal to R times F. R is the distances we've noted here. F is the weight. Let's do some calculations. We start with the torque just due to the weight of the arm. So let's label that torque sub arm. That is R times F, no sine of phi factor. The force that's applied is the weight of the arm. That's M times G for the arm. 4 kilogram arm times 9.8, 39 newtons. That's the weight force. The distance, 0.25 meters. So we can calculate the torque due to the arm, 9.8 Newton meters. That's what we start with. Next up, let's consider the torque due to the weight of the book. We'll call that tau sub book, the torque due to the book. It's R times F. F is the force that's applied. R is the distance from the pivot point. Well, we know the distance from the pivot point is 0.50 meters. We said that. But how about the force? Well, when I set up the problem at the start, I was holding the book on 2 hands. And so what we actually have here for the force, it's not the weight of the whole book, it's the weight of 1/2 of the book. So it's 1/2 times 5.0 kilograms. It's 5.0 kilograms divided by 2. That's just 1/2 the weight of the book. And we multiply that by 9.8 meters per second squared, which is g, and so we end up with a torque due to the weight of the book, 12 Newton meters. The total torque that we get is the sum of these two, 22 Newton meters. We were asked to solve for by what factor does the book increase the torque. So really what we're asked to find is this. We want to find how much bigger is the total than the original, which is just the torque due to the weight of the arm. So we're going to do the total torque divided by the torque just due to the weight of the arm. That's 22 Newton meters, divided by the original value, which was 9.8 Newton meters. So the factor by which the torque increases is a factor of 2.2. It's 2.2 times as difficult with the book as it is with the arms just by themselves. Let's take a look, see if this makes physical sense. If I hold my arms out like this takes a significant amount of work, actually, to hold my arms out like this, because there's the gravitational torque, which is pulling down my arm, and it's this far from my shoulder. Well, the tendons that are holding it up are pretty close to the shoulder joint. So this distance is pretty small. This distance is pretty big. And so the force that I have to apply in the tendons to hold my arm like this is actually bigger, significantly, than the weight of my arm. That's a point we're going to come back to in Chapter 8. But let's think about this. Just holding my arms out like this, that's pretty difficult. And if I take a 5-kilogram book and put it on the ends of my arms, what I find is this. That feels about twice as hard to hold my arms in place as just holding my arms out directly. That's about what we found. So physically, it makes sense, which is not a surprise. Physics is about the world around us.